Hello everybody. In the last class we had a look at basic logic gates, and we had seen representations of those logic gates or circuitry using Boolean algebra. So, we shall look more into the fundamentals of the Boolean algebra in this particular class. The concepts that we shall cover are Huntington postulates that are the basics of this particular Boolean algebra, basic theorems that are derived from it, and the concept of duality. We shall show some examples of these derivations of theorems and from the postulates, and also we shall discuss its difference with ordinary algebra. So, in the previous classes we are looking at two variable examples, two variable logic operations, right. And if we look at the two variable representation, so with two variables we can have two variable, we can have 2 to the power 2, that is 4 possible arrangements in the this truth table. So, this is 0 0, 0 1, 1 0 and 1 1. These 4 possible rows are there with two variables, okay. And for each of these cases we can have many different way the functions, Boolean functions can be represented, right. So, in one example, say all of them the output could be 0. In one, say output can be 1 only for the case when 0 0 is 1 and rest of the cases it is 0. Output can be 1 only for the case when input is 0 1 and rest of the cases it is 0. So, these are different possibilities, and how many such possibilities are there? Since it is there are 4, so 2 to the power 4, that is 16 such possibilities are there, okay. And with this among these 16 possibilities we are familiar with which operations? So, this operation we are familiar with, NOT operation, okay. That means when 0 0 is the input and 1 is the output and rest of these things are 0. So, we know this operation as A plus B prime, right, and corresponding its inverse is over here 0 1 1, right. So, we are familiar with this operation. So, this is A plus B. We are also familiar with this operation, and when both of them are 1, output is 1, right, and rest of the cases output is 0, this is 0. So, we know that this to be AB. This is next is NAND is just opposite of it, we know this to be AB bar, and some of this yellow marked one. So, you see that when x is 0, output is 1 irrespective of the value of y, and x is 1, output is 0 irrespective of the value of y, again these two cases. So, basically what you see here is x prime, okay, x complement. Similarly, this is y complement. So, that way all the different these combinations or possibilities, each of the function can be represented. This is 0 of course, and this is 1, okay, but rest of the cases we can have a corresponding Boolean expressions, right. So, this formalization of representation and manipulation is done by Boolean algebra, and in this case we saw for two variables we had 16 such possibilities. If there are 3 variables, so how many rows will be there in the truth table? 2 to the power 3, there will be 8 rows, right, and with 8 rows how many possible functions are there in this side? So, for one such combination, say function is 0, rest all the outputs are 0. In another case, only one case output is 1, rest of these cases are 0. So, that way 2 to the power 8 such possibilities will be there for 3 variable, okay. So, for any n variable cases we will be having number of rows 2 to the power 2n, right, here, and with that you can have 2 to the power 2 to the power n possibilities of arrangement in the form of Boolean functions, okay. So, this is we keep in mind, and we understand the importance of their representation and manipulation, and for which we shall have a look at Boolean algebra, and more on that is we shall discuss later. So, as I said, Huntington postulates form the basic premise of this Boolean algebra. So, it has got 6 postulates, Okay. And here we are talking about two valued Boolean algebra. So, it has got two elements, and these two elements are two unique elements. They are 0, 1, this is forming the set of B, right, and 0 of course is not equal to 1. And postulate 1 says that it is closed with operators plus, that is OR, and dot, that is AND operator. That means if you are having a operation with these two operators, the result is unique and is a member of this set. Okay, that is, the result will be 1 or 0. Identity element. So, for OR operation, the identity element is 0. That means x plus 0 or a plus 0, it is x or a. Okay, so it will be the variable itself. And for AND operation, the identity element is 1. That means ANDed with 1, it will be the variable itself. So, this is the second postulate. Commutative with respect to AND and OR operation, right. So, that is x plus y is equal to y plus x, x y is equal to y x. We have already seen this in the basic logic gate operation through truth table before. Okay. This is distributive over plus, that is AND is distributed over plus, that is x ANDed with y plus z is x y plus x z, x and y or x dot z. Okay. This is also, all of these can be verified from the truth table, and OR is also distributive over AND. So, that means x or y z is x or y and x or z. Okay. This is similar to what you see in ordinary algebra. This does not look like that of an ordinary algebra expression. Okay. This is one difference that we take note of. More we shall take note later on. Okay. Again, you can verify it by forming a 3 variable truth table and putting the values, and then calculating the output, corresponding output, and you can see that that is what you will arrive at. And finally, after these identity, TT, commutative, distributive, we come to complementarity postulate, where it says that if x is an element of set B, then there exists a x complement which is such that x plus x prime is 1 and x dot x prime, x and or x prime is 0. Okay. So, that is again one unique thing about a Boolean algebra, unlike the ordinary algebra, and we already see its corresponding meaning, significance. So, 0 plus 0 prime. Okay. So, 0 prime is 1, its complement is 1, 0 plus 1 is 1. So, similarly, 0 and 0 prime is 0 and with 1 it is 0. Okay. So, similarly, will happen for 1 plus 1 prime case and 1 dot 1 prime case, that you will get 1 over here and 0 over there. So, these are the basic postulates, and we note that associative law that we are talked about, that x plus y and it ORed with j separately, and x ORed with y plus y ORed with z separately, they are the same. This is not part of basic postulate, but it can be arrived at from the postulates that we have discussed so far. Now, with these postulates behind us, we take note of in the form of a table some important identities, which is very useful in case of this Boolean algebra based manipulation. Okay. So, some of them are directly derived from the postulate, some are represented as theorem, which can be proved by the postulates. Postulates are the axioms, self evident thing, and theorems and other identities are actually the one that can be proved from the postulates. So, they are given different names, okay, which is useful in some sense. Later on you can refer to it when you are using a particular kind of postulate or theorem to prove one particular relationship or simplifying a certain relation, certain algebraic expression. So, identity we have already seen. Okay, x plus 0 is x, x and 1 is x. Null, okay, this is a theorem, null theorem. So, that means x if it ORed with 1, anything ORed with 1 gets nullified. I mean, that has got no value. So, it will be the output will be 1. So, x has no representation in the output, and for the AND case it is x ANDed with 0, the output will be 0. Okay. So, this is can be derived, we can see later. And complementarity, x plus x prime is 1, x dot x prime is 0, coming directly from the postulate. So, the one that is in the brown are coming directly from the postulates, and the rest are the theorems which can be derived from the postulate. So, idempotency means it is remaining the same, that is x plus x is equal to x, x ANDed with x is also x. Involution. So, double prime, double complement is this variable itself. Commutative, we have already seen x plus y is same as y plus x and xy is yx. Okay. Associative, as I said, it can be derived from this, we have already noted. Distributive, coming from the postulate which we have directly noted before. And as I said, it can be the theorems can be developed from postulates. More such theorems we shall see later in the next slide. So, for example, let us take this null A, x plus 1 is equal to 1. Okay. So, this is x plus 1, then it can be ANDed with 1. Where from it is coming? This is coming from the identity B. Okay. This is coming from this one, the arrow is there, right, this one. Then this one can be written as x plus x prime. How can you write it? From complementarity. Complementarity A. Okay. Then you can use distributive property where x plus yz you are using, x is there is equal to x plus y and x plus z. So, this is x, this is your y and this is your z, this is y and this is your z. Okay. So, yz getting multiplied over here and this is x, okay, according to this. So, this x is there, yz is multiplied, x multiplied means ANDed. Okay. So, x prime ANDed with 1. Okay. So, then this is your this is your distributive B. Okay. And then again you use identity, this identity B, you get x prime, and x plus x prime is 1 from again your complementarity. Okay. Complementarity A. Is it clear? So, x plus 1 is equal to 1. So, that way all the these theorems can be proved. Okay. And if it is asked, you can write corresponding postulates or other basic theorem that you have used in the right hand side to explain the steps that you have taken to arrive at that particular proof. Okay. More theorems which is useful. One is called absorption. So, that is your x plus xy is x and corresponding form over there x ANDed with x plus y is also x. Adsorption, okay, x plus x prime y is x plus y, x ANDed with or version of x prime plus y is xy. Uniting xy plus xy prime is x and x plus y ANDed with x plus y prime is x. Consensus theorem, it is interesting, where you can see that there are 3 terms over there and there are only 2 terms over here. So, this term yz is not included in the right hand side. So, this is a consensus term, that means what is explained by yz in a truth table is already explained by xy and x prime z, for which you does not require another reference. So, that is why it can be simplified or it can be represented in this manner. Okay. And De Morgan's theorem we have already seen, and consensus theorem its other version in the product of sum version, it is called product of sum, because you can see all the products are there and this is sum version. So, x plus y x ANDed with x prime or z ANDed with y prime y or z, and this y or z is not required in the final expression, because this is a additional term which is already explained by other two terms. Okay. Now, in the previous case as well as in this case, you see that there are two rows A and B. Okay. One is representing in a SOP or sum of product form, another is representing it in a product of sum form. So basically the OR operation is done at the end, another case AND operation is done at the end. Okay. So these two expressions, if you just compare, and if you look at another interesting theorem which is there for Boolean algebra, all algebraic expressions remain valid if the operators and identity elements are interchanged. Okay. These are beautiful things about Boolean algebra. That means operators, okay, and identity elements. So what are the operators? Operators are AND and OR and AND. Okay, these are the two operators. So basically what you are telling by this, that you convert OR to AND to OR, identity elements 1 to 0 and 0 to 1 in any algebraic expression, right? You get a equivalent, I mean the identity will remain valid, the resulting identity will remain valid. Okay. So that is what this duality theorem tells. And if you compare the left hand side and right hand side of the two tables that we have seen so far, it is talking about that. Okay. I take this example, say the first one over here, right. So this OR is replaced with AND here, okay, AND is replaced with OR, and it is fine. The whatever resulting expression identity you get, it is also valid. Okay. So earlier we have seen for null 1, x plus 1 is equal to 1, right. We have already seen from basic postulates, we have seen. So now what you can do, if you apply duality, so this x AND changes to or changes to AND over here, one identity element 1 changes to 0 and 1 changes to 0. You get another relationship, that is x and 0 with 0 and with 0 results in 0. Okay. So this is also your that was there in the column B for the null. So this is also a very useful theorem which is which can be used for simplification and other cases. Okay. And to get you accustomed with the way you use these axioms or postulates and basic theorems, so we have a few more proof that we can quickly discuss. Okay. So idempotency that we started with, that we can have a we can see how it can be used in this particular case, right. So this x plus x, right, we would like to prove that same as x, right. So start with you AND it with 1, so that is the identity postulate. Then 1 can be written as x plus x prime, complementarity postulate, right. And this is your x, this is your x, this is your, you can consider this as y, and this you can consider as z, right. Then you can apply the distributive postulate, distributive law, and you can get x plus yz. Y is your x over here and z over here. So x prime you get, and then x prime is 0 from complementarity postulate, right, and x plus 0 is x from identity postulate. Okay. So the basic theorem related to idempotency can be arrived at by using the basic postulate. Okay. Similarly, idempotency B also you can arrive at starting with using the identity element, okay, then the complementarity, okay, then distributive, the other version of the distributive one, and the complementarity, and then finally the identity element, you can get the all the final proof of this, and you can also get it from duality also. Okay, that and is replaced with or, there is no identity element, so it remains same, x and x is x. Yeah. So similarly, you can look at the involution, the proof of involution, that is double prime is the function itself. Okay. So in this case, again you start with the plus 0, that is identity element, identity postulate. So complement, that is 0, can be written as x prime. Okay. So now this is the distributive law in the other direction. So from x plus yz, you are going to x plus y and x plus z. Okay. So this is your x, this is your y, and this is your z. So x, this is your y, corresponding y, okay, and this is your corresponding z. Okay. So you have to remember, I mean, you can sometimes you need to expand, for which also you can use the distributive law. From right hand side you go to left hand side. Okay. So after that, what you are doing, you are just changing. So basically it is commutative. Okay, for which you can change. So x comes this side and x prime goes to the other side, and similarly over here, right. So when you do that, you can use the complementarity, a plus a prime or x plus x prime is equal to 1. Okay. So after doing that, this 1 can be written just to help the help progressing with the proof. 1 can be written as x plus x prime, and then you can apply again distributive law over here. So this is your x, this is your y, and this is your z. So x is there, yz comes over here. Okay. So with that you get this complementarity postulate, you get 0 over here, and x plus 0 with identity postulate you get back 1 x. Okay. So using the basic postulates, you can get all the theorems that we have discussed. Okay. So we shall look at just 2 more proofs, the last 2 ones. Okay. So the consensus theorem, right. So in the consensus theorem, we have left hand side we have this term. So yz, we use the identity postulate. So we include 1, then complementarity x plus x prime we put in this place, then we just expand it. Okay. And then we use the associativity. Okay. So associativity is not part of basic postulate, but as I said, the basic theorem can be also used for proving a more complex expression. So this is the way you are doing it, right. And then if you just use take x y out, then 1 plus z comes over here, 1 plus y comes over here. So again 1 plus z is 1, that is again a basic theorem we have derived from postulates. Okay. So so this is your null postulate. From that you are getting 1, this is also getting 1, and finally you arrive at this particular version, okay, which is a simplified version of this. So this is your consensus theorem, one version, and another version you can get similarly or through duality. Okay. Through duality, just you have to change this and to or and this to and. Okay. And similarly here it will change to or, and this will change to and. So basically if you just do it that way for all the cases, you will get the corresponding version for the consensus theorem. And proof of De Morgan's theorem, it is done again, this is what we have seen in the previous case, that you can use basic theorems also along with postulates to derive the identity and or the proof. And in the De Morgan's theorem we do it in an indirect way. We can see that how it can be done in an indirect manner. So, the what we have to prove is x plus y prime is x prime ANDed with y prime. Okay. So, we already know that from the complementarity, the basic complementarity, x plus x prime is equal to 1. So, x plus y as a whole you can consider as x. So, this is already known, right. And if we can prove that x plus y and x prime dot and with y prime, this one that we seek to prove, we wish to prove is equal to 1, then we we can rest our case. Okay. This is an indirect way of doing it, but this is also can be used depending on the need. Okay. So, this x plus y and x prime dot y prime. So, basically we start with that one, and again you use the distributive law. So, this is your x and this is your y z kind of thing. So, x and this is x plus y and x plus z, this is the distributive law that you are applying, and then you are just, it is commutative. So, basically x plus y, we can write y plus x, and this remains the same. Then you can apply associativity. So, this is your associativity. So, basically instead of this grouping you are doing this grouping, okay. Instead of this grouping you are doing this grouping, right. And x plus x prime from complementarity is 1 and y plus y prime from complementarity is 1. Okay. So, you can then you can look at the identity null relationship. Okay. So, this is 1 and this is also 1, together you get 1. Okay. So, now we can see that this is true. So, the other one is also true. Okay. So, to end, we shall just this part of the discussion, we shall just look at some of the characteristics. So, what we have noted before, that the Boolean algebra has certain differences with ordinary algebra. This distributive law, the way we have seen it and utilized in many different cases, this is not valid for ordinary algebra. So, if you have got say like 5 plus 2 into 6 kind of thing. Okay. So, 5 plus 12 is equal to 17, and here if it is 5 plus 2 multiplied by 5 plus 6. Okay. So, you will get what? 7 into 11. Okay. So, that is not that is 77. So, that is quite different. Okay. So, this is not valid for ordinary algebra. Complement is not available in ordinary algebra, that we already know. It does not have inverses for addition and multiplication like subtraction and division. This kind of inverses are not there in Boolean algebra, okay, which is there in ordinary algebra. And Boolean algebra has this two-valued Boolean algebra, the one that we have seen, has got only finite set of elements 0 and 1. For ordinary algebra, there is infinite set of elements, I mean 0, 1, 2, 3, 4, the number can extend to any high value. And if somebody thinks that instead of and or operation, if we can develop Boolean algebra using NAND and NOR, it is not possible because the distributive law and some of these basic things, postulates are not valid using NAND and NOR. And earlier we had seen that we discussed that they are commutative, but they are not associative. So, we can just do a quick we now know how to use it. So, if we are talking about say an AND operation, okay, and then see this one, and if we try to check it with A, B, C and then AND, we shall see that they are not. So, we can expand it using De Morgan's theorem, and we can see that it will give you A bar plus B bar, okay, dot C, and then this bar. And similarly over here, if you just look at if you just expand it, you will see the the both sides do not match. In fact, what will match is the relationship like this. Here we have used this operator for NAND and this operator for NOR for better understanding. Okay. And similarly for distributive, as I said, they do not follow distributive law over each other. NAND is not distributive over NOR, or vice versa. NOR is not distributive over NAND. But if you check the relationship, then you will see that again using De Morgan's theorem, if you just expand it and put it together, instead of this x NAND y NOR z, the way I have put it in parenthesis, okay, it is x prime NOR with y, which y prime x prime NOR with z, which is when there is an AND operation between these two, then we shall get whatever is there in the left hand side. So, this prime operation, the complement operation comes here as well as here, here as well as here. So, that is why it is called pseudo-associative or pseudo-distributive. Okay. So, and we cannot use it in place of AND and OR operator in Boolean algebra. So, with this we conclude key points. In variables we can have 2 to the power 2n possible functions. 6 Huntington postulates form the basic premise or axioms of Boolean algebra, and the basic theorems of Boolean algebra can be arrived at from Boolean Huntington postulates, and these basic theorems and postulates can be used to simplify or prove different identities which is more complex in nature, and we can refer to those basic theorems and postulates. And it has got, Boolean algebra has got certain distinctive characteristics that differentiate it from ordinary algebra. AND and OR operations are associative as well as distributive over each other, but NAND and OR operations are not. Okay. Thank you.